Have you ever stopped to think about the world around you? I mean, really think about it. What if I told you that the solid chair you're sitting on isn't really solid at all? That at its most fundamental level, reality is just a shimmering dance of possibilities. Well, today we're diving headfirst into the quantum revolution, a wild story about how science completely shattered our old, comfortable view of the universe.
And wow, this quote really nails it, doesn't it? It gets right to the heart of this huge shift in thinking. The universe isn't a collection of tiny little billiard balls bouncing around. It's something much, much stranger. To really get it, though, we first have to understand the beautiful, predictable world that quantum mechanics completely blew up.
So I want you to picture a time when the universe felt, well, solved. It was seen as this giant, magnificent clock. Every gear, every pendulum, every single movement was perfectly predictable. That was the golden age of classical physics. But as we're about to see, that beautiful clockwork universe was about to crack wide open.
Back in the late 19th century, physics really felt like it had it all figured out. You had these two pillars of certainty. On one hand, you had Newton's mechanics, perfectly describing the majestic dance of planets and the arc of a cannonball. On the other, you had Maxwell's equations, which painted this elegant picture of light as a smooth, continuous wave. It seemed like we had the rule book for the entire universe. But a storm was definitely brewing.
Yeah, this perfect, harmonious picture started to fall apart at the seams. Because when scientists started peering into the tiny, tiny world of the atom, they found something deeply unsettling. The old rules, they just didn't work down there. The clockwork universe was starting to tick in a very, very strange way.
And then, boom, the bombshell started dropping. First, Max Planck discovers that energy isn't a smooth flow, but comes in these little distinct packets he called quanta. Then, Einstein comes along and proposes something that sounded completely insane, that light, the ultimate wave, could also act like a particle. And then, Niels Bohr's model of the atom, with its weird, rigid orbits, well, that was pretty much the final nail in the coffin. Physics was in crisis.
So into all this chaos and confusion steps this Austrian physicist, Erwin Schrödinger. And he comes along with this absolutely radical new idea. He proposed a kind of new music that could finally make sense of all the bizarre things happening inside the atom.
Inspired by this budding idea of matter waves, Schrödinger just asked this revolutionary question. He said, hold on a second. What if an electron isn't a little speck, a tiny solid ball? What if it's actually a wave, kind of spread out in space? This question sent him on a quest to find the mathematical score for this new music of matter.
And what he came up with, honestly, it was so much more than just an equation. It was like a spell, written in the language of math, a kind of secret key that would unlock the mysteries of the quantum world with just breathtaking accuracy.
Okay, now don't worry, we are not going to solve this thing today, but what's really important is what it does. You can think of it like a cosmic crystal ball. If you know what a quantum wave looks like right now, this equation tells you exactly what it's going to look like at any point in the future.
So here's the absolute heart of it. That psi symbol, the wave function, that's our star player. It's not a dot on a map, it's a cloud of possibilities. It describes all the places a particle could be. The Hamiltonian, that's basically the total energy of the system. It acts like a musician, plucking that wave function to produce a certain note. And just like a guitar string, only certain specific notes or energy levels are allowed.
Okay, but this is where things get really, really weird. I mean, truly mind-bending. Because Schrödinger's equation didn't just give physicists a new tool for calculations. No, it forced them to completely redefine what reality itself is. Remember that old Bohr model? The one that looked like a tiny little solar system with electrons zipping around in neat orbits? It was kind of comforting, right? It was a familiar picture. But as it turns out, it was just plain wrong. See, Schrödinger's equation just throws that whole idea out the window. It tells us that before we look for it, an electron doesn't have a definite location. It exists as this wave of potential, a cloud of pure probability just smeared out across space. So if it's not a physical wave, what on earth is this thing? Well, another physicist, Max Born, kind of cracked the case. He realized that if you square the wave function, you get the probability of finding the particle at any specific spot. The wave isn't made of stuff, it's a way of information. It's a map of where the particle is most likely to show up.
So this gives us this wild three-step dance that reality is always doing.
First, before we look, the particle is in what's called superposition. It's a ghostly blend of all its possible states at once. Then, the instant we observe it, that whole wave of possibilities just collapses. And finally, the particle snaps into one single, definite location. It's like our very act of looking forces the universe to make up its mind.
So, yeah, we're living in this fuzzy world of probabilities and uncertainty. It sounds kind of chaotic, right? But even in this strange new reality, there are some incredibly deep, unbreakable rules that still hold everything together. And these rules connect the quantum world to something even more fundamental.
And this brings us to something just beautiful. It's called Noether's theorem. And it's one of the most profound ideas in all of physics. It basically says that for every symmetry you find in the universe, there's a quantity that's conserved, something that never changes. For example, the reason energy is always conserved, it's because the laws of physics are the same today as they were yesterday, and the same rules apply tomorrow. It's that simple. And these deep rules are just as true in the quantum world as they are for us.
And get this isn't just some abstract idea on a chalkboard anymore. We can now actually watch this happen. An attosecond is a billionth of a second. It's an impossibly short slice of time. But using lasers that fire pulses that short, scientists can now create stop-motion movies of electrons. We can literally see these quantum waves evolving, which is just a stunning confirmation of these century-old ideas.
So, why does any of this matter to you? Because the quantum world isn't some far-off ivory tower concept. It is all around us. In fact, it's humming away inside almost all of our modern technology. The semiconductor chip in your phone, that's pure quantum mechanics. The laser in a Blu-ray player, you got it. Even the fusion happening in the sun, all of it is playing Schrödinger's melody.
So, this quantum revolution, it's given us unbelievable technology, but it has also left us with this deep and honestly pretty unsettling mystery. If reality is just this shimmering sea of possibilities until we look at it, then what in the world is going on when nobody's looking? And that's the question that still lies right at the very heart of physics today.